So we are now going to go ahead and discuss the domain of a function. The domain of a function is the set of all inputs, which we know as x values, of a particular function. So let's look at exercise 1. It says consider the function f of x equals 2x. Now, what numbers are you able to substitute in for x in order to get an output? These numbers are called the domain of the function. So if we have the function f of x equals 2x, we could really plug in any number for x and get some sort of output. No matter if it's negative, if it's positive, it just has to be a real number. So in this instance, the domain would be all real numbers. The symbol for all real numbers looks something like this. Now for part B, it says write the domain as a compound inequality. All real numbers can go on forever to negative infinity as well as to positive infinity. The way we write this as a compound inequality, we start out with negative infinity. Now, this number could be anything less than or equal to negative infinity, which is not possible, or positive infinity. So this is how we would write this as a compounded inequality. Now, using interval notation, we would use parentheses negative infinity to positive infinity because it's impossible to equal to infinity. If it were a number that we could equal to, we would use a bracket. Okay, so we will talk about that more in this next example with the graph. So for exercise 2, it says the graph of f of x below shows a function graphed over a specific interval. So we have this function that starts here with a closed circle, goes down and comes up and stops with an open circle. So then it says evaluate f of negative 6. So the way we do that, we go to negative 6 on our x's because domain talks about x values, and we match it up where it meets the graph. So the value, if we plugged negative 6 into this function, we would get 4. The next question says, is there an output for f of 3? If we go to 3 on the x values and follow it to the graph, yes, there is, and it's between 2 and 3. I would say that it's about 2.6. So yes, there is some sort of output for the input of 3. Now for f of 4, if we go to the graph and follow it, or follow that x value to the graph, it meets up with an open circle. If there is an open circle on a graph like this, there is nothing there. It does not exist. There is no output. So then for C, it says write the domain of f of x in interval notation. So again, the domain is the x values. How far left and how far right do the x values go? So this graph goes from negative 6 to 4. There is a closed circle on negative 6, so that negative 6 gets a bracket. It goes to the furthest point 4, which has an open circle, so it gets a parenthesis. So if you want to remember it like this, if there is a filled in dot, it gets a bracket. An open circle gets a parenthesis. And then D, it says write the domain of f of x as a compound inequality. So our most left is negative 6. Now, since it's a closed circle, it can be equal to 6. The furthest right is the point 4. But since there's an open circle at 4, it cannot be equal to 4. So we do not put that line underneath the inequality. If we move on to the next page, we have a couple more practice examples. So number 3 says consider the relation m of x, and we have a bunch of points here, negative 2, 0, 0, 3, 2, 6, and 4, 9. A quick review question, is the relation a function? Yes, this is, because there are no repeating x values. Then for B, it says, what is the domain of the function? So the domain here, we just have a bunch of points listed. This is not really a graph. If we put this onto the coordinate plane, we'd have a bunch of random points. So what we do for this is we list out our x values from least to greatest. So our domain would be negative 2, 0, 2, and 4, because those are all of our x values. For number 4, it says, for each of the scenarios below, explain whether the most appropriate domain would be all real numbers positive rational numbers, or whole numbers. So A, the weight of 7 different packages at the post office. This would have to be positive real numbers. That would be because all real numbers would include negatives. We cannot have a negative weight for a package. It wouldn't be whole numbers because a package can weigh in between whole numbers. It could have a decimal ending. So our only option is positive rational numbers. And again, we could have a package that, let's say, is 7.2 pounds. That would not be a whole number. Then B, it says the number of cars that drive through a given intersection. That would be a whole number answer because we cannot have a half of a car or a negative car. So all real numbers would not work. Positive rational numbers would not work. Whole numbers would be our only viable option. And then for C, we have the possible values of x that make the value of y a real number in the equation. So basically, if we plug in real numbers, positive rational numbers, or whole numbers, will we get a real number as a value of y? If we plug in any real number, we would get a real number output. So all real numbers would work for this one. Then for D, the distance traveled from a person's house to where they work, that would have to be positive rational numbers. And the reason being is, again, it may not be a whole number distance. We might not have 2 miles or 3 miles. It could be 3.3 miles. That would be a positive rational number. All real numbers would be negatives. We cannot have a negative distance. And then for the last question down here, it says the function c of x being 50 cents times x plus 125 represents the total cost of frozen yogurt for x ounces of frozen yogurt. An appropriate domain would be real numbers, rational numbers greater than 0, integers, or integers greater than or equal to 0. So rational numbers would include negatives, so that's not going to work for us. Integers would also include negatives. That's not going to work for us either because, again, we cannot have negative weights. Rational numbers and integers seem like viable options for both, but integers only include our counting numbers, 1, 2, 3, 4, 5, and so on and so forth. Rational numbers allows us to get that decimal. So we could have something that's 2.7 ounces. So the answer here would be rational numbers.